In this video, we will learn about the different types of utility functions and how the consumer attains the equilibrium. So we will take the Cobb Douglas utility function in this case. Okay, so let's take the Cobb Douglas utility function. That is, we have the first case of Cobb Douglas utility function. So in this case, what happens? It is general form. First we write the general form. So general form of Cobb Douglas utility function is that is, utility is a function of two goods, let us say x and y, and it is equal to x to the power a times y to the power b. This is the standard Cobb Douglas utility function, where x and y are the two goods and a and b are the two constants. Here a, b are the constants. Okay, so let us suppose their consumer is facing this kind of utility function, what we call the Cobb Douglas utility function. Now in this case, let us also assume that we have the budget constraint, that is price of x and units of good x plus price of y times units of good y, and it should be equal to the income of the consumer. Okay, so given this standard Cobb Douglas utility function, if the consumer wants to maximize his utility, so we will take utility utility maximization problem. So consumer will try to maximize his utility derived from the goods x and y, which is equal to x to the power a times y to the power b, and he will face some constraint that is such that price of x times units of good x plus price of y times units of good y should be equal to the income of the consumer. So our problem is, in case of Cobb Douglas utility function, we need to maximize the utility subject to the budget constraint. Okay, having said that, what we are going to do here, we want to find out the optimal bundle that the consumer will choose. Okay, so for optimality, the condition is that we equate the marginal rate of substitution between good x and y with the ratio of the prices, price of x and price of y. This denotes the slope of indifference curve, and this denotes the slope of budget line. Okay, slope of budget line. MRS, as we know from earlier videos, it is simply the ratio of the marginal utilities of good x and marginal utility of good y, and we equate with price of x and price of y. Okay, so to calculate marginal rate of substitution between good x and y, we take the ratio of the marginal utilities, and we know that marginal utility of good x is the change in the utility due to the change in the units of good x consumed divided by MUY. Likewise is the change in the utility due to the change in the consumption of good y. It should be equal to the ratio of the prices, that is price of x divided by price of y. Okay, so let us take a simple graph here also to make things clear. So we have good x on the horizontal axis, good y on the vertical axis. So let us suppose consumer is facing this budget line, budget constraint. So this is our budget constraint. With the given budget, consumer wants to achieve highest satisfaction, and this condition actually is a point of optimality, the point where the indifference curve and the budget line is tangent. That will give us the optimal units of good x and y. That will give us the x star and y star. So x star denotes the demand function also of good x, and y star denotes the demand function of good y. So we need to calculate that very thing. So we have, so this is a point of tangency here. So it is also called the tangency condition, where the marginal rate of substitution between good x and y is equal to the ratio of the prices, price of x and price of y. So px py denotes the slope of this budget line, MRS is the slope of the indifference curve. So du upon dx, that is the partial derivative of utility function with respect to x. We need to find out. We have this utility function. Let's take its partial derivative with respect to x. By using power function rule, exponent of x becomes coefficient. So we have a times x, and exponent is subtracted by 1. Y raised power b remains the same because we are taking partials. Okay, so that's the partial derivative of utility function with respect to x. Likewise, we take partial derivative with respect to y, so it will become b, x raised power a remains same, but the exponent of b will be subtracted by 1, and we equate it with the ratio of the prices, price of x upon price of y. We will also solve a specific problem here. Okay, so let me try to take the general form here. Okay, so doing some simple algebra, we can write it like this. So let me write it here. So we have a upon b. Okay, so transpose this y to numerator. So we have y raised power b first here, and when we transpose it here, so it will become y raised power minus b plus 1, because when we transpose denominator to numerator or vice versa, exponent sign changes. Likewise, we have x to the power a here. If I transpose this x to the power a minus 1, it will get multiplied, but it is exponent will change. So if we have a, it becomes minus a, minus 1 becomes plus 1. Okay, so I am just solving this stuff here. Here bases are same, we can add up the exponents. So we have a upon b, y raised power, so we have b minus b plus 1, and in the denominator we have same basis, we can add the exponents. We have a minus a plus 1, and here you can see it is a upon b. B and b gets cancelled, we are left with y raised power 1, and here we are left with x raised power 1, which is equal to a upon b times y upon x. Okay, so when we solved this thing, we got a upon b times y upon x is equal to px upon py. Okay, now I can rub this out. Okay, let us solve it for y first. So if I solve it for y, and let me solve it here, so we have a upon b. Okay, or let us solve it step by step. So we have y upon x first is equal to, transpose it here, it becomes b upon a, px upon py. Okay, now transpose this x, so we will get y is equal to b upon a, px upon py times x. Okay, so we got here y is equal to b upon a, px upon py times x. Rather, okay, so we solved it. I don't have space, that is why I am doing the calculation here. Now we plug this value of y into the budget constraint. So let us plug the y here. So we will get price of x times units of x plus price of y. In place of y, we have now b upon a, px upon py times x. So py gets cancelled, and we can take x first common. Okay, x and px. If I take x times px common, we will be left with 1 plus b upon a. Okay, and it should be equal to the income. Usme mashti go magaz us khabar kape. Solving further, so x times p of x, so it becomes a plus b upon a is equal to m, or we can write x is equal to, so we have m here, transpose this here, it gets divided, so we have a plus b upon a. If I transpose it, it becomes a divided by a plus b. So here, okay, that means x is equal to m times a divided by a plus b px. This is the demand function for good x. Okay, We also call this Marshall and demand function. When the demand is a function of income and prices, we say it is a Marshall and demand function. Okay, so this is our demand function for good X. Likewise, if I plug this value in this equation, we will get the optimal bundle for Y will be equal to M times B divided by A plus B times BY. Okay, this is how we solve rather the optimization problem, rather constrained optimization problem, when the individual is facing a Cobb Douglas utility function. Okay, so let's take the specifics here. Okay, let me take a simple example here. Let us suppose we have a consumer, so we want to maximize utility of the consumer, and let us suppose utility function is X times Y. So it is in the standard form here, A and B is 1 and 1 here, such that let us suppose price of good X is, let me write it here, Px into X plus Py into Y should be equal to M. Let us take price of good X is 1, so we have X plus price of good Y, let us take 2 times Y should be equal to, so price of good Y is 2 and it should be equal to income. Let's take any arbitrary income here, let us say 12. Okay, so using this equation, how do we solve it? So first order condition for optimization requires that rather we take the tangency condition, we equate MRS with ratio of the prices. MRS, as you know, it is the partial derivative of utility function with respect to X. Partial derivative with respect to X gives us as Y. Partial derivative with respect to Y gives us as X, and it should be equal to the ratio of the prices. Price of X we take 1. We have assumed here it is equal to 1 upon price of good Y is 2. Solving for Y, Y will be equal to, transpose it here, it becomes X upon 2. Now we plug this value of Y into the budget constraint here, so we will get X plus 2, so value of Y is X upon 2, 2 gets cancelled and it is equal to 12, so 2x is equal to 12, that gives us X will be equal to 6. So consumer will consume 6 units of good X, and how many units of good Y? So Y will be equal to X upon 2 means 6 upon 2, which is equal to 3. So Y is equal to 3. Graphically, what is meant by this? So we have X on the horizontal axis, Y vertical axis. We have this budget constraint and we got the optimality at this point. At this point, consumer will consume 6 units of good X and 3 units of good Y. Okay, in this specific case. So this was about Cobb when the consumer is facing Cobb Douglas utility function. In the next video, we will learn about the what we call, so let us take a linear utility function when the consumer is facing the linear utility function. Okay, so see you in the next video. Thank you.